Okay, this is 7.1 in your textbooks, page 330. So it's a very short lesson today, guys. So hopefully you'll be able to get all your homework done in class, and you'll have 2 days without homework. Okay, so we did have the test yesterday. We're looking at similar triangles, investigating properties of similar triangles. So before we can learn what similar triangles are, first we have to know the definition of what congruent figures are. Congruent figures and similar figures. So congruent figures have identical shape and the same size. So can anyone tell me, what is the point of saying something is congruent? Why not just say it's the same thing, the exact same triangle? Is there any way or reason or rhyme of reason that you can think of why congruent figures might be important, or when it could be confusing as to whether or not a figure is congruent? No. So it's almost so simple, it's almost confusing in that sense. Congruent figure, it's the same figure. The only area where I tell you to be careful with congruent figures, and I've drawn it specifically this way, the triangle is exactly the same, because they are exactly the same. The only way you can get confused, though, is if, see, I already did draw a little bit different there. It's exactly the same figure, so I have to draw it exactly the same size. Okay? But one of the things to note is that the orientation can be off. Okay, so that's the only trick with congruent figures where you could get confused, is that these two objects here and here are congruent. Why are they congruent? Because they're the exact same size, okay, and they have the exact same shape. The only thing that is different between the two is that the rotation is different, okay? And that's where it comes in, rotation and translation and dilation and those different things, where we rotate and reflect. You can have the exact same figure but a different rotation and still have to be congruent. Okay, so that's the only area where you may get confused with congruent figures. But essentially it's the exact same shape and size. Alright? With similar figures, however, we have identical shape, so the shape looks the same, but the size, the third one is always the same because of our properties of triangles. 180 minus the other two angles, the third angle is going to be the same. But that's very important to know. So angle U here is equal to angle B, which angle T here is equal to angle A, and then angle B is equal to angle C. Okay, so I have the same orientation here as well. Although this triangle could be completely upside down, but still be similar. Okay, so don't confuse rotation with size or with shape. Okay, so the rotation can be different. So that's one property of a similar triangle, is that all the angles have to be the same in the two triangles. The other property is that once we know that, the ratio of the corresponding sides are equal. So AB, which is this side, AB right here, that is going to be equal AB over TU.
Pardon me, teachers, I'm sorry. Mr. Portrini's period 4 class, could you meet him in the cafeteria now? Mr. Portrini's period 4 class?
So the ratio of the corresponding sides are equal. Doesn't mean that the sides are equal. These sides are not equal. But the ratio of this side over this side is going to be equal to the ratio of this side over this side. Okay, this is the most important part about similar triangles. And this is where all the questions come in. When you're comparing a small triangle to a big triangle, you use these side ratios that are equal to determine the unknowns. Okay, so this is always true. If you have similar triangles, all three angles are the same, the ratio of the same sides are going to be equal. So the only trick here is making sure that you pick the identical side. So if this has a different orientation, you might put AC over TU. Okay, that's going to be wrong. You have to have the same sides over each other. And the best way to determine that and make sure you're doing that correctly, again, because the orientation can all be backwards or upside down, is use the angles. If you're talking about the side TU, you're going from angle 0 to angle X. Make sure you're talking about the same side in the bigger triangle. You're going from angle 0 to angle X. Okay, that's the only way you're not going to get confused when you do this. Okay, it looks simple here because I have them in the same orientation, but make sure you use that side over that side is equal to this side over this side, which is equal to this side over this side. And the only other trick where I've seen guys go wrong is that they'll confuse which triangle they're putting on top. Okay, so they might say that this side over this side is equal to this side over this side. That's wrong. You have to be consistent with which triangle you put on top for the top side ratio. Okay? Those are the two kind of things I've seen that go wrong with similar triangles. So if you're going to say the big triangle, maybe you always say the bigger one is on the numerator. Okay? You got to be consistent when you say, okay, this is the ratio I'm going with. This side over this side is equal to, now this side over this side. Don't switch numerator and denominator when you're switching from triangle to triangle. Okay, so those are kind of some of the mistakes I see people make. Let's look at a typical problem now. So this is example 1 on 331. It says, identify a pair of similar triangles and explain why they are similar. Support each statement with a reason. So we have a person standing here in front of a tree. Okay? And I hope that by just looking at this, you can envision two triangles in this main drawing. Okay? One triangle is inside the other triangle. And this happens a lot with this section. All right? The triangles are not always completely separate, as you saw in the previous example. A lot of times, one triangle is contained within another triangle. And right away, because of that fact, you see that two angles are the same. So you can see, or at least one angle is the same, because that angle is in both triangles. It's in this larger triangle here, and it's in this smaller triangle here. Okay, so I've broken those out. This triangle here, x and p, is here, x and p, and the larger triangle, x, e, t, is here, x, e, t. Okay, so that other little triangle is in there. But these two now are similar triangles. Okay, any questions about that? Yeah?
Are two angles the same because they both have 90 degrees?
Yeah, you're right. So this angle is contained. The only thing I was mentioning is that the similar angle that's in is actually, this is the only one that's contained in both. Like it's the actual identical triangle. You're right. All three angles are actually the same in both triangles. You're right. But this is the only one that is contained in both triangles. So already as you're starting, you have one angle that's exactly the same. Okay? All right, so we have two triangles now here, two similar triangles. We're going to list some different properties here. So when we call out angles, if I want to talk about this angle, okay, there's several ways to do it. Sometimes you can just say angle P. Okay? But when that doesn't work is if you have, let's say, another angle in here. Okay, let's say there's a line like this. So now you have, two angles that are really starting at angle P. So that's why we don't use that nomenclature. We don't call this angle P. How we do call it out is we call it out by all three letters. Okay, so this angle is going to be angle XPB. Okay, and the angle that you're talking about is always in the middle, but these other two letters point out the full angle. Okay, the full direction. Okay, just to show that again, we have something like this. Okay, I just want to just explain why we have this nomenclature. If I say just angle P, I don't know if it's this angle I'm referring to or this angle. Okay, that's why if I want to call this angle out, I say angle APB. Okay, that means I'm talking about APB, this angle. If I want to call this angle out, I say angle BPC. Okay, BPC. And it wouldn't have mattered if I called it CPB. The important one is the P in the middle, and then you've called out the direction of the angle. Okay, so that's why we use this nomenclature. So, angle XPB is going to be equal to what angle is the same on this triangle using that nomenclature that I called out. Dominic?
XTE.
Excellent. Yeah, angle XTE. And why are they the same?
Because they're both
90 degrees
Good, they're both 90. How do we know they're both 90?
because of the square.
Yeah, the square, good, I drew that. But if we're going back to the original problem, how do we know that those two angles are 90?
I don't know.
It's not an easy question because it's a bit of an assumption. Andy?
So the bottom line, we could assume that it's a straight line,
Yeah?
and we assume that both the person and the tree are going directly vertically.
Standing straight up, yeah, you're right. Yeah, so it's an assumption. Okay, it's not an easy answer. It's a bit of a trick question there. But it is assumed that this person is standing straight up. That's how we know that these are 90 degrees. Okay, and then when you have any questions like this where there's a building or a tree, always make that assumption that from the ground it's 90 degrees up. Okay, don't put that argument on a test, well, I don't know if the building was built correctly. We're going to always make that assumption. Yeah,
Did you say not to make assumptions in math? No?
did I say that?
Pretty sure you said that like.
Okay, well, this particular case, make the assumption. All right? Shouldn't really assume, kind of, in most subjects, I wouldn't say not just math, but not always great to make assumptions, but in this particular case, in these problems, make the assumption. Okay? It's 90 degrees. All right, next angle we want to look at. Let's look at this angle x. So angle PXN is equal to angle TXE. Okay. Everyone understand this nomenclature now, right? Anybody confused by that? I didn't spend a lot of time, but it's important. If you can't call the angle out correctly, then I can't give you the full marks, because if you call the wrong angle out, then you know, it's going to be wrong. So make sure you understand how to call it out. So PXN is equal to TXE. How do we know that? Ace. How do we know that this angle, PXN, is equal to TXE? Yeah, because they're the same angle, right? Yeah. So we know they're the same. Why? Because they are the same. It's the exact same angle, okay? Because one triangle is within the other. All right, and then the last one, angle X NP is equal to X E T. Okay? How do we know these two are the same? Daniel? How do we know this angle is equal to this angle?
They're the same triangle. They're similar triangles.
Yeah, that's what we're trying to prove. We're trying to prove that by telling us all the angles are the same. So you can't jump to that conclusion. How do we know that this angle is the same as this angle?
Because if the bottom line is straight and then at a 90-degree angle, the top line both goes up by the same.
Yeah, you're right, but there's a better kind of a better answer. It has to do with the properties of a triangle and three angles in a triangle. Do you remember?
If two are the same, then the other one.
Exactly. Yeah. So we know that these are the same because why? Because all triangle angles add to 180 degrees. So with that logic, if two of them are the same, the third one must be. Okay? But I know what you were saying. It's the same line, so it's going to create a same angle with the vertical. You're right there too. Okay? Good answer. All right, example 2 is my last one, and then you guys should have plenty of time to finish your homework. Example 2. It says, are the two triangles in the diagram similar? Explain your reasoning. So we have a diagram that looks like this. It's a river. You see this quite often, this style of diagram. Okay, we have a bunch of sizes here. Okay, and these are all labeled B, E, C, A, B. All right, so we want to know if this triangle is similar to this triangle. Luigi, based on the definition of similar triangles, what do you think you're going to focus on in this particular problem? Are you going to focus on angles or side lengths?
Side lengths, because
Why?
they're given.
Yeah, because they're given and you don't know any of the angles, right? Well, that's not true. We know some of them, right? We know that this angle has to be equal to this angle, right? And assuming that these shores are parallel, we know that through Z theorem that this angle is equal to this angle. And then if we know two are the same, we know the third one. So we could prove it using angles pretty quick as well. Okay, but there is a bit of assumption, I guess, that this shoreline is parallel to this line. So let's use side lengths instead. So Luigi, what am I going to do with my side lengths? How am I going to figure that out?
Well, you know that DE and over AB is equal. No,
So DE over AB, okay, yeah.
yeah, and CE over AC are equal.
CE
Wait, no,
over AC. Okay, so I agree with you. I think from the way I'm looking at it, you're right. But the most important thing is here that you need to kind of orientate the triangles in the same way so that you don't make a mistake and put the wrong sides over each other. Okay? I think Luigi did that though. So he saw in this triangle, DE, if I were to flip this triangle over like this, that's going to be the top X, DE is going to be the base, going to be the same as AB. So DE is using the larger triangle first over AB, so DE is the height, the base over the base, is equal to CE. Now he's using the kind of angle is going to be equal to AC over the little one. So I'd agree with that. Daniel, you had a comment?
Alright?
You had your hand up?
Oh no, I was just gonna say there's a 1 to 5 ratio between the triangle.
Okay.
Because you can tell by the one side.
You're right, yeah, you've seen that, just the 5 and the 25, right?
Yeah.
Yeah, we're going to find that out as we plug in the values. Good, so finally the last one then, what's Luigi, what's the third side?
It's equal to DC over BC.
Excellent. So if all these ratios are equal, then we know they're similar triangles. So let's now just fill it in. DE is 20 over AB is 4. It's equal to CE, which is 25 over 5, which is equal to DC, 15 over 3. So this is 5 is equal to 5 is equal to 5. All right, so because all the ratios of all the sides are equal, then therefore this must be similar triangles.